Hello guys, welcome back. So today for the higher levels we're going to focus on electrolysis because I think it will encompass a lot of the skills that you'll see in the higher level section. So the first part is multiple choice, and then the second part is a free response or extended response type question. Pause the video if you want to try. Try them now. I'm not going to read it out because it would take a while. Pause the video now if you want to try and come back for the solution. Alright, so for the solution, for the first part, let's draw out a table. Now, I know we don't have our standard state cell potentials. However, drawing a table out and listing all your options is a really good idea on even on the multiple choice section of an exam, or writing stuff out, because oftentimes when you write stuff out it becomes clear, oh it's this or oh it's that. So let's write out a little chart. And for electrolysis, I always first I draw out this table where I put cathode and then anode. The second bit I always consider is, the second thing you should always ask yourself is this a molten salt or is this a aqueous salt? If it's a molten salt, your life is pretty much made easy because it's just the half reactions associated with the ions of each salt either oxidizing or reducing. It's sort of, if you know how to form the net ionic equation, the net equation to form the salt, it's just basically backwards. And it's just the half reactions associated with going backward. And your life is made easier. Now, unfortunately, we are told that this is 1 molar aqueous NaCl. So now we have to do a little bit more to consider because water itself can undergo electrolysis as well. So, red, ox. I just write that down just to remind myself what's what. So, let's first start off with the possibilities on the anode side. And so we know at the anode either sodium can even chlorine can oxidize, so 2Cl minus produces Cl2 plus 2 electrons, or we could have oxygen oxidize, so we would have O2 minus 2O2 minus yields O2 plus 4 electrons. And then on the cathode side, we could have either sodium reduced, so plus electrons yields Na, and then we could also have hydrogen reduced, so H plus 2 reduces to H2. Now, this isn't technically the right ones, but however, for all intents and purposes, on a multiple choice exam, generally this is what you want to come up with. Now, the way I go about it is sort of like this. So first let's consider the anode. So we want oxidation, and in order for something to oxidize, generally the things that are stronger reducing agents or easier to oxidize, they generally have low electronegativities and low ionization energies. Now, in this case, chlorine and oxygen are both on the non-metal side of the table, and they're basically right next to each other. No, they're not next to each other, but they're pretty close, and therefore they sort of behave similarly. But what you want to do here is know your periodic trends. Since this is in a lower period, lower row than oxygen is, it means that its ionization energy is lower and its electronegativity is lower when compared to this. So this is what forms at the anode. Now, an exception to that is that although this is technically more thermodynamically stable, when this is highly concentrated, it's much faster because it's a one-step reaction rather than the sort of 2 steps the official one is. But for paper 1, the logic is that, okay, this is less electronegative, this is a lower ionization energy, therefore this is what's produced at the anode. Now at the cathode, we want sort of the opposite of that. A good oxidizing agent will have a high electronegativity and will have a high ionization energy. So we're using electronegativity here. And of these two, of both sodium and hydrogen, it's clear that hydrogen has the higher electronegativity than sodium. So therefore, this is what gets produced at the cathode. So the answer, according to our little, according to, so the answer would be C. I wonder if it's possible to highlight that. So the answer is C. No, bad. Oh god, that's bad. So the answer is C. Home. So the answer is C. Right. Now let's do the second question. The second question is again split into two parts. Pause the video if you want to try it, though I'm sure I already asked you to. So here's the solution. Now, like we did for the last one, let's first draw out a little chart here, just to sort of, let's draw out a chart. And so, anode, cathode. Red. So, reduction. So, the possibilities we always want to consider are both that of water and of our solution. Now, let me first pull up a table. You need a table of cell potentials. So, let me just pull up my handy dandy little table of cell potentials. So, here it is. Here's our table of cell potentials, which we'll use that later. Link is always in the description to the set of notes here. It would be under file 3.19. And there's a table of half cell potentials. So the first thing, so let's consider each electrode separately. So at the cathode, we could either have 2Cl minus 2 plus, no, not that, whoops. At the anode, that occurs. At the cathode, we could have lanthanum 3 plus 3 electrons reduced to lanthanum. Or, according to our table here, we could have water is being reduced, so we could have 2H2O plus 2 electrons yields H2 plus H minus 2, and this yields a cell potential of both, and this yields potentials of, for lanthanum, it would yield a potential of, if I can find it here. Okay, well, for water it yields a potential of minus 0.83 volts, and for lanthanum it yields a potential of God, where is lanthanum on this table? Excuse me, guys. Here. Control F. No, it's not here. Okay, lanthanum 3 plus, that is minus 2.37 volts. And then for the anode side, we can either have 2Cl minus reduced to Cl2 plus 2 electrons, or alternatively, water itself would get oxidized, so we need to find one where it's just, where we would get 2H2O yields 4H plus 4 electrons plus O2. And there's another one there that there was another reaction that we could also consider. It was like, I think it had a lower cell potential. It was like negative 1.7 something. Yeah, negative 1.78. It would be just, the other one we could consider here is H2O it's H2O2 plus 2H plus 2 electrons, and this one has a potential of negative 1.78 volts. Now, in practice, you'll almost always just consider this one, and you'll never really think about this one. You'll only think about that one. And let me finish in the cell potentials. For the other side, the potentials are negative 1.23, and the one for chlorine is negative 1.36. Now, since we weren't told that the concentration was dilute, we're going to assume it's concentrated, and because of that, although this is slightly more stable than that one, because it's highly concentrated, this is a single step reaction, whereas this would probably be a bunch of steps, and therefore, because of that, this one occurs faster, so it would be this one that's chosen, and then here we just compare the numbers, and the least negative one is the one that's chosen. So in this case, it would be this one. So our overall equation would be, when we add the two up, the electrons, how conveniently they balance out, we get 2Cl minus plus 2H2O yields H2 plus 2OH minus plus Cl2. And that's the answer to our first part. Now let me just clean the board up a little bit. We're going to get rid of that. We will get rid of that eventually. So let's move this up top here where I can work. Alright, so that's the answer to the first bit. Now for the second bit, we are asked, how long will it take for all the chlorine gas to fully electrolyze? So how long will it take for all the chlorine gas to form? And we are told that there was half a liter of 1 molar, half a molar. Now, there it was. One, two, three, four, five. 1, 2, 3, 4, 5. Before, after, and we are told that 0.5 liter 1 molar La. So we are told that there's half a liter of 1 molar of that. Now we need to find the concentration of chlorine ions, right? So in order to find the concentration of chlorine ions, we would know the number of moles of chlorine ions, so we would do 0.5 times 1, which is 0.5. But remember, since there's 3 chlorines for every mole, 3 chloride ions for every mole of salt, we should need to multiply this concentration by 3 because it is triple. So there's 1.5 mole of that, right? And now we can do a little dimensional analysis. That's our friend here. And I forgot to give you Faraday's constant. That's in your data booklet, so no fret. But so let's do a bit of dimensional analysis in order to work this out. So we know that 2Cl minus yields Cl2 plus 2 electrons, and we need to oxidize it. And it turns out I forgot to give you some information. So let's say it was running I forgot to give you some information, so let's give you that information right now. I just realized of 1 amp 1 at a current of 1 amp. Yep. So at a current of 1 amp, how long would it take? So when I do dimensional analysis, the first thing I want to do is consider the thing that is not a conversion factor. So we know that we produce 2 moles of electrons for every 2 moles of chloride ions, so that's good. So 1.5 mole Cl minus, and we know that according to our reaction, we yield 1 mole electrons for every mole Cl minus. And then I know that for a mole of electrons, we run it. A mole of electrons is 96485 coulombs for every 1 mole electrons. And then I know that an amp is 1 second for every coulomb. And that should yield an answer that is equal to, so 1.5 times 96485. The answer is it should take about 144,000 seconds. So 4 times 10 to the 5 seconds. And that's our answer. And we can check to make sure that our units work out. So mole of chlorine is gone, mole of electron cancels, and coulombs cancel. And I intentionally wrote it in such a way, so I know an amp is a coulomb per second, and I intentionally did it in such a way such that our units canceled. And yeah, thank you very much for watching. Don't forget to like and subscribe.